Welcome back to today's discussion of the normal approximation for probability histograms. We've done lots of problems using the normal approximation, and when doing these problems, you should have handy your standard table. So your Z table, of course, there's one in your book, or use the one that I provided. This is an important tool for solving problems related to probability histograms. Fortunately, most of our problems for today many of them are pretty conceptual. Let's look at number 1. The figure below shows the probability histogram for the total number of spots when a die is rolled 8 times. The shaded area represents the chance that the total will be between 20 and 25. That's right. This is inclusive, so it's going to include 20 and 25, and you can see that it starts here at 19.5 and proceeds. 10 draws are going to be made at random with replacement from the box 0, 1, 2, 3. Here's our box. The chance that the sum will be in the interval from 10 to 20 inclusive equals the area under here are our options, between and blank. So we have 3 blanks here. It's always best when you're doing a fill in the blank to make sure you read the whole question before you start filling in blanks. So not as essential with this one, but certainly a good advice. So the chance the sum will be in the interval from 10 to 20 inclusive. We're talking about chance now. So the chance that the sum, is it going to be under the normal curve or the probability histogram for the sum? This is going to be the probability histogram, because the normal curve is the approximation, the histogram is the truth. It's okay, this is a little tricky. We're gonna get the hang of it. And what are going to be our range of values for an inclusive area between 10 and 20? Well, we're going to want to start just below 10. So B will be 9.5. And C, we're going to want to go just above 20. So we'll have 20.5 on the top. Our next problem looks at 25 draws made at random with replacement from the box 1, 1, 2, 2, 3. One of the graphs is a histogram for the numbers drawn. One's the probability histogram for the sum, and one is the probability histogram for the product. Which is which? Well, let's look at these. We can see that having just looked at the probability histogram for products, I think most of us can recall that the product histograms have this distribution shape that's quite abnormal. So this is going to be our probability histogram for the product. Now let's look at these other two. We have one is going to be the histogram for the numbers drawn, and another is the probability histogram for the sum. Which do we think number one is? In this case, this is going to be our probability histogram of the sum, exactly, because here we have a probability histogram clearly, and this is looks quite similar to our other probability histograms. And this 3 is our histogram just for the numbers drawn, which makes sense because we would expect the numbers drawn to be 1, 2, or 3. In the next item, we can look at a pair of dice. The total number of spots is like either one draw from the following box or the sum of 2 draws from the box 1, 2, 3, 4, 5, 6. Let's all vote box 1 or 2. Box 2. Very good. This is a pair of dice are like the sum of 2 draws from the box 2 because each die, excuse me, has its own, is independent of the other one. Putting them together in the box on 1, the values have equal chances, but that's actually wrong. As we know, 7 is more likely, for example. Finally, we have a problem with 900 draws made at random with replacement from a box with 99 tickets marked 0 and 1 ticket marked 1. True or false, and explain. Let's look at the first one. The sum will be around 1, give or take 1 or so. Is this true, A, or false? I'm going to go with true. Why is this true? Because there's 100 draws made at random from a box with 99 tickets marked 0 and 1 ticket marked 1. So if we want to get our expected, remember that our expected value for the box it's okay. And we could prove this with expected value and standard error calculations. But we are kind of limited for time. But if you want to see that worked out, go ahead, and the standard error or the expected value and standard error will bear out to be 1 and 1 respectively. Let's look at part 2. There's about a 68% chance that the sum will be in the range 0 to 2. What do you think? It's false. Very good. There's not a 68% chance here. You don't have enough draws to use the normal approximation. Remember, this is just 100 draws. So we just can't use the normal approximation at this point. And let's just go ahead and quickly do this. So we can see that for this box, remember the expected value this is good practice. So we'll just go ahead and do this. Review. Expected value is equal to the mean of the box times the number of draws. So what's the mean of this box? It's 1, because if we sum, it's 0.01, and then it's going to be, because we would take the sum of all of our zeros and 1. So the sum of x is going to be 1 over our n is 100. So the mean of the box is, but then we're going to multiply it by our number of draws and end up with 1 for our expected value. And how do we get our standard error? Well, the standard error of the box, the sum of the box, that is, equal to the square root of the number of draws times the standard deviation of the box. The square root of n, remember, is, our n is 100, so the square root of n is going to be 10. And our standard deviation is, we could work it all out here, but remember there's 100 draws, so I'm not going to have you work out a standard deviation for 100 of any, by hand, that is, for 100 draws, we would, so don't worry about that. But to give you the standard deviation of the box here, we know it's going to be it's 0.1. On an exam, in case you're wondering, sure, I would give you the standard deviation in this if this were an exam problem, which it is not likely to be. So don't worry about exactly calculating the standard deviation across 100 draws. But you can see if you use the standard deviation of 0.1 times your standard error, square root of 100, you're going to end up with a standard error equal to 1. Okay. And our last item here, we have 100 draws made at random with replacement from the box 1, 2, 2, 5. The draws come out as listed. And let's fill in the blanks here. Here are some options. Sum of draws, number of ones, number of twos. Okay. For the blank, the observed value is 0.8 standard errors above the expected value. What do you think is going to go here? Well, let's think through how we can address this. It would be helpful to know the sum of the draws, right? The sum of draws in this case, if you work out the sum of these draws, it's 270. But remember, the sum of draws are observed, so it's going to differ from the expected value. Our expected value, as we recall, is equal to the average of the box times the number of draws. And you can see that the expected value would be 250 here. The average of the box is 2.5 times 100 draws. I'm sure you can easily work out the average of the box in your head here. And finally, we have a standard error, which I'll give to you. It's 15. We can see that the number of ones is actually 17, but which we'll label observed value. But the expected value for the number of ones would be 25. Why? Because 100 draws are made at random with replacement from this box, 1, 2, 2, 5, which means that our expected value would be 25. Now, ones are 1/4 of the box. And the standard error here, you could certainly work out. It'll be approximately equal to 4.3. And we can do the same for our number of twos. We observed 54 twos. But our expected value for twos is 50. And a standard error with a standard error equal to 5. Now, for each of these observed values, we can figure out exactly what the chance error is, because we know the observed value, the expected value, and the standard error. So if we look at the sum of the draws, The chance error is 20. Our observed minus expected is 20. And we can figure out the position, the corresponding standard score for our observed value. And in this case, the standard score would be 1.33 standard errors. Okay. I'm sure you'll see if you work out the standard error using the expected value, you'll end up with a standard error of 15. I think that, Sarah, you might be using you might have used the sum of draws instead of the expected value. And I would be happy to work it out, except for time. We really, I don't want to go through the standard deviation calculations, to be honest, because we really do need to get through chapter 19 at minimum today. So our number of ones, but this is an important idea here, how we're representing these, the error from the box in our standard scores. So let's look at the number of ones. We have an observed value of 17. We know our expected value was 25, and our standard error was 4.3. Of course, we can get our chance error here. Chance error, we're just using the observed value minus the expected value. Oops, that should be an EV, sorry. Observed 17 minus 25. We're going to end up with a chance error here about -8. We'll call this chance error. And we could convert our observed value to a standard score, and it's equivalent to a standard score of -1.8 standard errors. And finally, for 2, same process. So our chance error here is going to be clearly our observed value, 54 minus 50, our expected value. So chance error will be 4. And that's 0.8 standard errors. Now we have got lots of numbers, right? But what do we do with them? Well, let's fill in the blanks. For one of these groups, the observed value is 0.8 standard errors above the expected value. Where did we see an observed value 0.8 standard errors above the expected value? we can see clearly here that that was in number of 2's. And for our second blank, we want to find the group with an observed value that's 1.3 standard errors above the expected value. This is clearly in the sum of the draws. This problem gave us a good practice finding the expected value, remembering that the observed value is different from the expected value, and we can use the observed value to, in conjunction with our expected value and standard error, to get the exact chance error and then the standard score, which, as you know, our standard errors can be very useful, and there's many applications of standard units. As we'll see, we'll carry many of these ideas forward in our future topics. Remember, for the most effective way, do some statistics every day.